PCB fabrication.
Okay.
So this first panel that we're showing is Interlayer Image. A typical interlayer image, if it is not a blind via that would have to require an additional oxide process, actually is pre-procured with a zinc or a brass oxide on it. We get the cores with the zinc or brass oxide on it. Back in the old days, we had to run through an oxide process. It was a black carbon process. And what do we use it for? It's for adhesion promotion, or a tooth for adhesion promotion in the lamination stage. That's really all the zinc or the brass oxide is for. The inner layer, as you'll notice, and I apologize for this sort of latent image, what you'll see is when we get into the area, you'll see that it's a nice dark blue resist. I almost wish we would have done it with a nice dark blue resist, because the offset would have been, the contrast would have been so much better. But the darker image you see there is the resist. The resist is actually covering your desired copper features. In this case, a ground and power. This layer, the ground side, on the opposing side of the core would be the power layer. You'll also notice this venting pattern that we have on there. We call this a starburst pattern. If you've been in any other PCB manufacturer, you would normally see a series of dots around the periphery of the board. Both of them are adequate and both of them work. And what's it for? It's to provide a path to evacuate the prepreg once it becomes its gelatinous state. Once it reaches its T sub G and starts to flow out the panel in lamination, these are to be able to provide a path for all of that prepreg material to come out. Makes a big mess around the outside edge. We call it flash, and we remove the flash after we've gone through the lamination stage back down to the original panel size. We operate two panel sizes, 18 by 24 and 12 by 18. And what we need from you, image area, is 1 inch less all the way around due to the tooling that resides on the periphery of the boards. They live at approximately 750 thousandths, so we just call it an inch. We'll say, okay, for a 12 by 18, we need a 10 by 16 usable image area for you. Or if you had a larger board, we could put it on an 18 by 24. Your usable image area for that would be 16 by 22. So we can pretty much encompass most sizes of boards. Most boards these days are anywhere between 4 by 4 to 6 by 8. DIMS, SIMS, MIMS cards are even an inch by 5 or 6 inches long. Stuff like that. So we can usually accommodate any kind of a board size on one of our two panels. The next thing that you see is after we have imaged it, we do interlayer is what is set up as what's called a print and etch. Again, this is not a blind scenario where we've actually drilled holes in the core and gone through a plating process and actually created an interconnect on an interlayer core. This is just the centermost core prior to lamination and prior to actually drilling the through holes in it. So the next thing that you see is interlayer strip and etch. So we'll basically strip the resist off and etch, or actually etch the panel and then strip the resist off, this dark latent image that you see there. So now your copper is starting to really take shape. This is the actual 1 ounce, 2 ounce, half ounce copper of the board itself. You'll also notice that we have coupons on the side, on the periphery of the boards. These are standard class 2 coupons. The class 3 coupons are a little bit smaller and encompass a few more aspects. Peel strength, where to match the hole size of the majority of your component hole on that side. So when we get back to the testing area, or dry lab, if we call it, then we'd have all of those points set up and they can make measurements based on those things. The other thing I'd call attention is we have a series of concentric circles, and you can get a little closer on this, and if you can't see these, it's a series of concentric circles that are out around the periphery of your board. In the old days, 10, 15 years ago, to get a drill registration to your image, we would laminate everything together, and then we would take those panels into drilling. We'd drill a few holes, we'd take it out to the etcher, we'd etch off the copper, and we'd look at it and say, oh, okay, I need to make a zero correction, 1 mil this direction, and a half a mil direction this way, to center that drill image in the image that has just been created. We don't have to do that anymore. Now everybody uses X-ray machines. So we'll actually pilot a hole in these concentric circles and make any zero corrections that are necessary for the board on there. So we don't toast any panels through production by actually having to go out and etch a panel to do that process. The next thing you'd see is, in this case, it says double trait laminate, but it's actually a dark color. This would actually be a brown or a zinc, a black oxide. And what is oxide? It's like you lit a match underneath a book and you get that carbon buildup. That carbon is acting as a tooth or a little bit of surface aggregate for adhesion promotion at the lamination stage. It's so the layers will grip one another really well when we laminate the interlayers together. Again, the demonstration encompasses a 4-layer foil cap construction. So whereas I talked about copper foil on the outer layers, if we put copper foil here and here, it would wrinkle up and look like garbage in no time. Half-ounce copper, quarter-ounce copper foil is so prohibitively thin. Every time I'd come by and do a demonstration and touched it, it would be wrinkles all over the sides. So in an effort to kind of mitigate that, we put up core. This is intended to represent copper foil, but what you're actually looking at is very thin core. So this would be drum side or oxide side up. You'd have a B stage material. This is the resin impregnated glass cloth, like a surfboard. In fact, when we talk about signal integrity, we talk about various preg plies that are used for various line sizes. 5 mils is a great line size. Most people want to use for a 50 ohm structure. They'll say, okay, I got a 5 mil line for 50 ohm structures. What sort of a dielectric is necessary to do that? Well, it's certainly not a 14 core or a 13.5 distance that we would use on a standard 4-layer board. It's actually closer to about a 3 mil dielectric. And the general rule of thumb is the thinner the dielectric of the B stage material, the higher the resin content and the lower the glass content. The higher the resin content, the lower the decay. So what's another thing that also lowers the decay of a board? Speed. You know, if you're looking at 500 meg versus 10 gig, I guarantee that 10 gig board is driving that dielectric constant way down low. So I may say, okay, it's going to be 3.9 for the dielectric constant at 1 meg here or 5 meg here. At 5 gig, it's going to be maybe 3.3 or 3.6. And I'll give you a whole slew of those things when we come to do more and more business, and you see that I can provide you with calculations and stack ups and core material types, and all of the effective dielectric constants of all of the subsections, because they are different. I frequently get a phone call and someone will say, okay, Mark, what's the decay at 5 gig of P370HR? It depends on what the dielectric is. So it's not one number. It might be that we'll use one sheet of 106 and one 1080 in combination to make an approximation of about a 5 mil dielectric to meet the impedances that are being called out. At which point, the number that's in the book has to be blended with that. The one might be 3.9, the next one might be 4. So I may call the combination of those two pregs 3.95, something like that. So there is no one number to be used for the dielectric constant of any given material in the world. And there's hundreds of different materials out there, as you guys know. We're talking, you know, anything from IT180, P370HR, FR408HR, NP175, Rogers materials, which have very, very low dielectric constants and very, very low loss tangents. In fact, that's the whole reason people typically use a Rogers material is for the DF. They don't really care about the dielectric constant of the material. They want to know what the loss is. It's a very low loss material, so they'll use a ceramic fill. Yes?
Well, my experience is before we really start the layout, we go to you with our intent, and we give us back the material in line with and so on. Right?
Exactly.
That's the best place to start with the reasons we're talking about.
And you'll typically call it out as 4101/126. We use 4101 as a spec that describes the material constraints based on board class. So if you say, okay, I've got a 4101/126 material that tells us we can use IT180 or P370HR or FR408HR. We can use any of those three. Now, if you have a preference, call it out. Say, I need to have FR408HR. It's what I've been used to. I've got good numbers on it. I think I can stay within 10%. And remember, the goal for signal integrity is just get it close. That's all you got to do is get within 10%. The fabricator is going to take it X amount further. If I'm going to have to take your 5 mil line and change it by 1/4 of a mil and make it 5.25 to meet that 50 ohms, I'll do it. If I have to bust 2 mils I'm going to get a hold of you and say, I had to increase it to 7. And you may not even have air gap to be able to accomplish that. So that's where it becomes a negotiation, if you will. And you'd say, okay, what about this material? That you can stay closer to your original intended line size by doing that. That's a really good point. Again, copper foil, B-stage material, layer 2 on this side, layer 3 on the opposing side, more B-stage material, more copper foil. We're going to squeeze it and laminate it together under heat and pressure. It's a 375-degree process for a period of about 90 minutes. And we're going to go to each of these areas and talk about the same thing that I'm talking about now when we get to the area, just a reminder. But typically that's the process time. It's about a 90-minute cycle time at 375 degrees. We shoot for about an 11-degree rate of rise and a 6-degree cool down. What does that mean to you? It means that we're cooling down for twice as long as we are ramping up the temperature, all in an effort to not make potato chips out of your boards. And using very thin dielectrics in conjunction with very thick dielectrics in the same stack will tend to make potato chips. If you had a 4-layer board and you had 4 core or 5 core between layer 1 and 2, and 47 core or 50 core between 3 and 4, that 50 core doesn't want to move, but that 5 core sure as heck does. So in order to mitigate that, we'll run in additional extra press pads, steel separation units, and steel cold plates to be able to keep them nice and flat. In conjunction with that, we also use what's called post-etch punch technology. Are you familiar with that? 15, 20 years ago, an engineer said, well, okay, all the cores behave differently through these aqueous processes that we put them through in the wet process area. So because of that, not only are we imposing a scale factor, but wouldn't it be great to mitigate this movement in the registration of the lamination area by punching the tooling, this Lin-kite tooling, these 2 slotted squares and these 2 slotted squares and these 2 slotted rounds after we've done the processing. And sure, that works great. So we'll process an inner layer with no tooling on it. It has no tooling on it. We'll bring it back into the dry film area. We put it on a machine, and it's got these targets that are, well, they're not on an inner layer, they're on an outer layer. On an outer layer, and it would take those cores, auto-center them, and punch those Lin-kite tools, the 2 slotted squares, or excuse me, the 2 slotted squares and the 2 slotted rounds. See what I mean by the slotted rounds? This one has a radius associated with it. That one has a radius, and those are nice square corners in a rectangle. They're 187.5 width. And it's the standard in the industry. Everybody has been using Lin-kite tooling for years. It's spelled Lienkite. I believe it was the originator in Asia that came up with it and said this is the tooling process. It's the same tooling process that we use today. After we have laminated everything together, again, it makes a big amount of flash. We'll remove the flash, and we'll take your NC drill file that you've given us, and we'll drill the holes. Now there's a couple of different things that we've got that are on this panel that are redundant, that we still put on, and we don't need them anymore. And I'll tell you why when we get to the drill department. We have Schmoll machines from Belgium, so they are literally electrically affixed to the panels when we put the panels down prior to drill them. We'll put a piece of cooling material, it's called slickback material on the bottom. Then they'll stack up a board, and then they'll put a piece of aluminum separation material on the top. Why the aluminum separation and why the slickback? Why would we do that? Well, we don't want to drill directly on the copper surface and create burrs. We'd rather have it pilot through the aluminum, so when it actually gets to the copper of the board, it leaves no burrs. Why the slickback? The slickback is actually a composite material that cools the bits. The general rule of thumb is the smaller the bit size, the faster the spindle speed. The faster the spindle speed, the more heat is being generated through the process, and the more it smears the pre-preg material, those glass fibers and that epoxy in the barrel of the hole. So that's why we go through a composite stage. It removes that, it makes a nice conical wall. It removes those glass fiber bundles that protrude into the holes. It cleans up the resin on the sides of the walls, and then we put it in a catalyst, into a catalyst pre-dip, and then we put it into the Q-posit bath. And the Q-posit is, it's an acid copper bath, much like the plating bath, but it only lays down, because it's not an electrowinning situation where we're stimulating with power and actually pulling copper from the copper balls in an anode-cathode situation and plating onto the surface, the plating process. Because Q-posit is just an acid copper bath, it only lays down about 4/10 of a mil in the barrel of the hole and on the surface of the panel. And it's this stage right here, it's the Q-posit stage. So one of the things, I digress, I want to get back to the drilling. So one of the things that we always used to add was called a snowman. It went from the largest tool size to the smallest tool size that you use. And on the old Exelon machines, where they had tool pods, it would pick up this size, it would go out and drill that size, it would return it to the tool pod, it would pick up the next size. And the idea was, the last hole of that size would be over here on the snowman. So if we broke a bit somewhere of this size, it would be conspicuously missing on the snowman. So the operator would have a clue, I need to look on that panel somewhere for a broken bit. But as I mentioned, the schmoles are literally electrically affixed to the panels. So now, if we break a bit, it stops, a red light goes off, we pull the panel, pick the bit, and it picks up right where it left off. And again, we don't toast any panels, much like we did when we were drilling a few to match the image to the drill image. We don't have to do that anymore. Some other things that I'd call attention to is we have 2 sets of 125 holes in one corner and single sets of 125 in all the other corners. What does that mean? What's that all about? The 2 sets of 125 holes, or what we call dummy holes in the industry, are all they really talk about is that's where your board origin is. That's where your 0 corner is. So when you see 2 sets of 125 holes, that's the corner of your board origin. That's all it is. Additionally, you'll see out here on the corner, you'll see packs of very small 9-hole telemetry. So the idea there is we use a direct image device. Back years ago, we used to take a piece of silver film and we'd plot a piece of silver film on our photo plotter. We'd take that silver film, we'd take it into a photo area where we would shoot it onto a diazo chloride coated piece of film. And the reason we did that is because diazo had a little bit more resilient surface. So if you scratched a panel across it, it wouldn't remove the emulsion and wipe out a bunch of traces like it would if you did a silver film. So we would use this diazo chloride piece of film to actually laminate or put it on top of the photosensitized cores, and with high intensity ultraviolet light, we would image those cores. We don't do that anymore. Today we use direct image devices. We're literally drawing on the photosensitized cores with light. And you'll see the DI machine. That'll be one that you'll definitely want to see and get some photographs of when we get to that area. So those are the things that we would talk about in the drill area. Again, we go into the Q-posit area, and the Q-posit goes through a series of cleaners, conditioners, and then it goes into a catalyst, and then it goes into the Q-posit bath. Again, what we're looking for is a nice salmon pink on the surface and in the barrel of the hole. The problem with this is, and God bless him, is our general manager decided every time you go through here, you put fingerprints on these panels, and it drives me crazy. So he coated them all. He coated them all with a clear lacquer. Well, this is not the color of a Q-posit panel. If you look on the side, it's glossy. It would not be glossy. It would be a nice matte salmon pink. And by spraying it, he oxidized the holes. Those holes are black. That's clearly a reject panel that's hanging on the wall here. That's not exactly what it should look like. I understand his intent, but it's not exactly what that process looks like. Now, when we get to the outer layer image, we do it in the dry film again with a DI machine. And ultimately, it's exactly the opposite polarity that you had your inner layers. The inner layers, we had the photosensitive resist that was protecting all of your copper features, your plane layers, your signal layers, all of that stuff was protecting those copper features because it was called a print and etch. We would print it, etch it, and dry film strip it. On the outer layers, you'll notice all of your desired copper features, all your lands, all your surface mounts, all your holes are now exposed to the elements. This should make sense to you because this is where we're going to make all your interconnects. This is where we're going to plate the barrel of the hole and the surface of the panel to make all the interconnect connections. This is where the rubber hits the road, so to speak. This is where we're really going to actually plate the process on the surface and in the barrels of those holes. Now, one thing about holes that I'd want to talk about is let's say you provide us with a drawing, it's got 30 tool sizes, you got an 8 mil hole called out as ±3. What do we drill that at? We drill at an approximation of 4 or 5 thousandths larger to be able to plate back down to that nominal hole size. Now, let's say you had a situation where we ran into a problem on your data. We got your data and we were looking at it and we said, okay, we've got 8 mil holes. They're called out as plus or minus 3, but you've got 14 mil pads associated with them. Now, typically we'd like to ask for an approximation of 10 thousandths larger than your finished hole size, or an 18 mil pad. Now, can we deal with that 14 mil pad and that 8 mil hole? Yes, we can. What we would ask for at that stage is 2 questions I would have for you. One is, are those just vias? And you come back and you said, Daryl says, yeah, they're vias. They're fine. That means that they need continuity, but I don't really care what you finish them at. Therefore, I can drill them at closer than that 8. So then we change the tolerance to +3, -8, the entire size of the hole size. That clues the fabricator in. These are vias. We can drill them at whatever size we need to be able to deal with meeting the minimum 2 mil per side annular ring per IPC 6012 and 6012 class 3. That's what they ask for. They say, I need a minimum of 2 mils per side annular ring. So that's the way we would get around that. Outer layer image, again, is the opposite polarity of the inner layer image. This is where we're going to image that. Now, one thing you'll notice is, after we go into the plating tanks, we immediately go into a tin tank. What's the tin for? Why not that bright, shiny copper that you would see it coming out of the tank as? Well, tin is a sacrificial metal. The tin is on there to go over the top of the plated entities to hold it in place while we run it through an etcher. So the next thing would be to take this through the copper tin plate, resist strip, and again, I apologize for this latent image. This darker image that you see here and the lighter image that you see here, that's actually the color of the Q-posit. This is the color of the resist over the Q-posit. So we would run it through a resist strip to take the resist off, exposing all of that 4/10 of a mil Q-posit copper surrounding the tin plated protected features that are all plated up in the barrels of your holes, your surface mounts, and everything else. What this allows us to do is now run this through an etcher and etch off that background, and leaving only the tin protecting your desired copper plated features. And again, that should make some sense, because let's say we didn't do that. Let's say we didn't put that tin on there and we plated it up to this nice size here, and we've got a level of copper over the top of this Q-posit copper, and we run it through an etcher. Everything would be gone. Everything would be gone. All your traces, the barrel of holes, everything, we'd etch it all off. So the tin is a sacrificial metal only used to be able to protect your desired copper features before we actually resist strengthen, run it through the etcher to take the background Q-posit off. Then it's a simple matter of going through a 2-part tin strip where we'll take the tin off the surface. Now your board's really starting to take shape. We've got registration internally, all your layers are lined up. We've got through-hole plating, we've got surface plating. Now it's a simple matter of running through an LPI solder mask, or liquid photo imageable solder mask process. This says hot air leveling. It is not a hot air level board, clearly. This is an immersion gold board. Again, our general manager didn't switch out the tags. This is clearly an immersion board. It should say immersion gold, not a hot air level board. Component ID and final fabrication. So in a nutshell, that's the build of a board. Now what we're going to do is we're going to go to each of the areas and talk about what we do in each of those areas to make those things work.